We talked about heating curves earlier, where we would have a graph that looked something like this, and we would label solid, liquid, and gas, and we would put melting point and boiling point. Here we had temperature, and here we had heat added. Well, if you take that graph and turn it into I don't want to say a 3D picture, but a more expanded picture, you come up with what is called a phase diagram. If we were in class, what I would do is I would say, here are 3 different points. This is pressure, this is temperature. When someone measured the pressure and temperature at that point, it was the gas. When they measured it here, it was the liquid. When they measured it here, it was the solid. If you were to map out the entire temperature pressure range, what you would come up with is a phase diagram, and it represents a closed system. All right, so there's a lot on this picture. So when we have a line such as this is going to be called the freezing point, melting point. When we have a line such as this will be the boiling point. And remember, the transition occurs from one phase to another along a boiling point, same with a freezing point. So this diagram helps predict what can happen. We have one other portion here, which is the sublimation deposition. So think back to the endo and exothermic processes we spoke about when we talked about energy changes. Now, if we are on a line, we are going through a transition. It could be a melting, it could be a boiling, or it could be a sublimation. If we are not on a line, that is a single phase. Everything here is the solid, everything here is the liquid, everything here is the gas. The graph between the vaporization and condensation ends at a point where we can no longer turn it into a gas, whereas the line between melting and freezing goes on to infinity. So here I have it in words. It couldn't all fit on one page. Those curves represent dynamic equilibrium of 2 phases. That liquid gas curve, that is the boiling point, and we taught the normal boiling point is 1 atmosphere. If I'm on the liquid solid curve, that is called the melting point, and the normal melting point is 1 atmosphere. These are the facts you need to solve problems. And on the next slide, I show the change in slope. But to finish it up, the solid gas curve, that is the sublimation. So those are what the curves represent. They represent a dynamic equilibrium, and we often show that by those double-headed arrows. There's a couple other points. There's another point called the triple point. That is where all 3 phases coexist. So if I draw my phase diagram, here is my triple point. It's where I have solid in equilibrium with liquid in equilibrium with a gas. Remember I said that this line, the melting point line, goes on into infinity, but the line that represents boiling point has a definite stop, and that is called the critical point. That's the temperature of which the liquid state no longer exists regardless of pressure. And that is how they make decaffeinated coffee. That's how they make freeze-dried potato chips. There's a lot of different things that you can point to for it. But before we go there, okay, we have water and carbon dioxide. We have their phase diagrams, and they have bit difference of appearance. You see different pressures and different temperatures. But the thing I want you to note is when I have water, I have a negative slope. When I have carbon dioxide, I have a positive slope. When a scientist looks at a phase diagram and they see, let's first do the positive slope. What they observe is the density of the solid is less than the density of the liquid. Think about when you have some iced tea. The ice is floating at the top. That's because the density of ice is less than the density of liquid water. Well, with CO2, normally I do a demo. Can't do a demo in my house, don't have any CO2. But if you were to do CO2, what would happen is the chunks of CO2 would sit in the bottom of the CO2. So when a scientist sees a graph with a positive slope, they know the density of the solid is greater than the density of the liquid. I just really feel hamstringed by trying to do this online. You can do it so much better in person. I always have used this little picture, and this is nothing against dogs or cats or anything, but it's to talk about the process of sublimation, where we definitely go from the, well, let's read what it is. Freeze-dried Fido, man's best friend. Well, this is from the Wall Street Journal, and rather than have your pets stuffed when they die, what they're doing is they're freeze-drying them. Maybe you've seen it on one of those science shows where they put like an elephant or a camel into a freeze-dry chamber. But what it does, it evaporates the water directly from ice to a vapor. So we're saying we had a solid, we're taking it all the way to the gas phase, and then the vapor evaporates, and we never, ever, ever turn it into water. That's sublimation. This was used to preserve blood plasma in World War II. If you've ever taken something out of your freezer and seen things a little bit white on the edges, that's freezer burn. But that is how they preserve potatoes in the Andes Mountains, because the pressure was so much lower in the mountains. They were able to preserve, and it's how they make instant coffee. But if you were to take a mammal and you wanted to preserve it, those are the conditions that you would use. Again, just a little aside to make this just a tad more interesting. The other part where we talked about the critical point, when you get to that point, you have something called a supercritical fluid, and it becomes an excellent solvent. You can vary the temperature and pressure very carefully. When you have a high density supercritical fluid, it will dissolve something. When you have a low density, it'll separate it out. And I'm going to use the term OEM, original equipment manufacturer. That is how they paint refrigerators, stoves, washers, and dryers. The EPA does not like us putting toxins in the air. So if they're able to use a supercritical fluid, usually it is CO2, they are able to paint things in the factory in a much more environmentally friendly process. Little did you think this chapter would have any application. So what I usually do is I ask students to draw a phase diagram. I don't get to write the exam anymore, but I still like to show this in class. Here's my pressure and temperature, and essentially what I do is I draw a line that represents 1 atmosphere. Then what I ask students to do is to please put these points on the diagram. We're just going to roll through them. What I'll do is I'll put my melting point. Let's put my melting point here. It's the normal melting point. It's at -5. Let's put our normal boiling point. It says that it is at 85 degrees centigrade. Again, I don't worry about the scale. I just want to get you an idea of how they make these things. The critical point, it says it is at 130. And it is at 1.6 atmospheres. So I'm just going to put a line right here, and it's not going to be to scale, but I'll say that this is the critical point. And then the other point I want to put on here is the vapor pressure of the solid. At -30, again, we'll change the scale, it is 0.16 atmosphere. So what I've been able to do is construct a phase diagram. And the question that I would always ask students is, if I have a transition, let's say I have a gas at 50 degrees centigrade and I increase the pressure, how many phase changes would I go through? So let's say this is my point. Let's say it's 50 degrees. Let's say it's like, oh, I don't know, 0.5 atmospheres. And what I'm doing is I'm increasing the pressure. If I increase the pressure, I will turn that gas into a liquid, and I will do 1 phase change. Why ask these kind of questions? Well, my last slide on here is actually an MCAT question. As you see, there are the 2 diagrams, and there are a series of questions that need to be answered. Now, my current students have said that you get 7 minutes for this passage. Well, if you only have 7 minutes, you definitely have to go in knowing something about phase diagrams so that you can easily see what's going on. So let's just choose one. At figure 1, at -78 and 1 atmosphere, what will CO2 exist as? Will it be a liquid? I hardly think so. Equilibrium between gas and liquid? Equilibrium between liquid and solid, no. So those are the kind of ways that you will need to use these if you're taking a professional exam.